All right, so this first problem says a marble rolls off the top of a 1 meter high table and hits the floor at a point 3 meters away from the table's edge in the horizontal direction. How long is the marble in air, and what is the speed of the marble when it leaves the table's edge? Okay. So okay, so they tell you that you launch the marble with a horizontal velocity. So its initial velocity is horizontal, and the only force acting on the marble when it's in flight is the acceleration due to gravity, which is 0I minus GJ. Okay. And when this is the only force acting on it and it's a constant force, the trajectory is a parabola. We've learned that. Okay. Now, you guys understand that the greater the speed with which you launch, the further out it will fall. Okay. So from this distance, you should be able to calculate the speed. Also, well, this distance will depend on the speed and the time of flight. The longer you are in flight, the further out you'll fall. So that distance depends on two factors. Now the time of flight will depend on how high you jump off. The higher you jump off, the longer you'll be in air. Okay? So they've given us these two factors. They've told you how high you're jumping off and how far you fall. Okay? So you should be able to calculate the speed and the time of flight. Okay? Now, the time of flight depends on how high you jump off of. Okay? So you got to keep that in mind. So how long is the marble in air? That's the time of flight. Okay? And that'll be related to this distance. And what is the speed of the marble when it leaves the table's edge? So once you have the time and this distance, you should be able to calculate that. Okay? All right, now we'll write this in vector notation. Okay, what does this mean? That's your speed, and your velocity only had an x component. Okay? There's the acceleration. All right, so let's do how long was the marble in air. For the time of flight, what we'll do is we'll look at the y component of the equation. Oh, by the way, so you always draw your axes. There's my origin, there's the x-axis, and so on. Okay. Y minus y naught equal to v naught y t plus 1/2 a y t squared. Okay. Again, we're getting the time of flight from looking at the y component of the motion. Okay. There's the final y position. Here's the initial y position. This is 0. That is 1 meter. What is this? V naught y? 0. It's the initial y component of the velocity. That's 0. And what is ay? Negative g. Okay. So 0 minus 1 equal to 0 plus 1/2 times negative g t squared. Okay, so you can see that 1 equal to 9.8 over 2 t squared. And here I'm not writing down units, so this is meters. Again, it just gets messy. So this is 1 over, this is 4.9. Okay, so 1 over 4.9 equal to t squared. Okay, so here's an equation, and you can solve for t there. Now,
Just the one on the
I'm sorry?
Because you're doing 0 minus 1 equals that, so shouldn't that be a negative 1?
Yeah, this was negative, this was negative. Yeah.
Sure.
Yeah. So T equals and so plus or minus 0.45 seconds. Okay. And of course, our solution is okay, so our solution is this one. Okay, what is the negative solution? Okay,
Beforehand.
I'm sorry?
It would be beforehand, but would not.
Right,
start
right. So if you had thrown it from the ground level at the right speed and such that it was that speed, it would have started off at minus 0.45 seconds. That's what the solution is. Okay, so that's where y is also 0. Okay, so that was the other solution. All right, so we have the time of flight now, and now we'll look at the x equation and get v naught. Yeah. So now let's
I have a question.
yeah.
So like, how do you, like in like the part A, how did you get like, because you had the 1 equals the 4.9 t squared, like did you multiply the 2 to both sides, or how did you get rid of it?
This one,
Yeah, how did you get rid of 2 on the bottom of that?
9.8 divided by 2 is
Oh,
4.
you did it, okay, I get it.
Mhm. Yeah, I skip steps. I'm so used to it, so I don't even know I'm skipping steps. So if you don't ask, I won't realize it. Okay. And remember, you've already paid for it. But also, the counterbalancing argument is you got to let the class flow as well. Okay. All right, now let's look at the x component of the motion, x motion. All right, x naught, the initial x position is 0. That is 3 meters, the final x position. V naught x is just V naught. And AX is 0. Okay. So whenever you have these two-dimensional problems, set up your velocity like that, initial velocity like that, set up your acceleration, set up your axes. Okay. All right, so this was 3 minus 0 equal to V naught T plus 0. Now, so see, we already found T in the first part of the problems, and now you can solve for V naught. All right. So again, so let me show mathematically. We've ended up finding two things. We ended up finding V naught and T, the time of flight. And we had these two data points, the vertical distance traveled and the horizontal distance traveled. And from those two data points, we were able to find those two things. Yep.
And so for the horizontal distance, why does the second term automatically become 0?
AX is 0. X2.
Oh, okay.
Yep. And what is the speed when it hits the floor? So, okay. What is the direction of the velocity? Do you guys remember? Well, okay, so let's start off. What is the trajectory? What is this? This is part of a parabola. The trajectory is parabolic. The velocity at any given spot is tangent to the trajectory. And they're asking you for the speed, they're asking you for the magnitude of this velocity. All right, so C is, the final velocity is Vxi plus Vyj. Okay, so we have to calculate the two components. So Vx is V naught x plus Axt. All right, so final Vx is initial Vx because Ax was 0, and we just found that that is 6.67 meters per second. Vy was V naught y plus Ayt. What is the initial y component of the velocity? 0. Ay is negative 9.8 meters per second square, and the time of flight was 0.45 seconds. Okay? So this was equal to 4.41 meters per second. Okay, so the final velocity is 6.67 I minus 4.41 J meters per second. And you see, this is a vector in the fourth quadrant. And as you can see from the diagram, that is true. Okay? That's a vector pointing in the fourth direction, fourth quadrant. And well, what is it that you want? You want the speed, so you want the magnitude of that vector. So 8 meters per second. Okay. So this problem says an airplane flying horizontally with a speed of 500 kilometers per hour at a height of 800 meters drops a crate of supplies. If the parachute fails to open, how far in front of the release point does the crate hit the ground? Okay, so just like last problem, in the last problem, this height was 1 meter. Now we've just gone a little higher, 800 meters. In the last problem, they gave you the horizontal distance and they asked you to find the speed. In this problem, they give you the speed and they're asking you to find the horizontal distance. Okay? So instead of one thing, they're asking you the other thing. Okay? So the givens are the height and the speed, and you want to find the horizontal distance. Okay? Again, you'll need the time of flight, how long you're in air, and the time of flight is, of course, obtained from how far were you released from. Okay. All right, so let's set up our equations again. Okay. And before I do this, see, this initial speed is given in kilometers per hour. Let's convert that to meters per second. Okay. So 500 kilometers per hour. Okay. And you have to convert this to, so you have to multiply by the appropriate factors. But here's a quick way to do it. A kilometer is 1,000 meters. So that's 500 into 1,000 meters. And what is 1 hour in seconds? Seconds, okay? There you go. So you see that's, well, 3,600 divided by 1,000 is 3.6. So all you do is divide this by 3.6. Okay, so it's 500 divided by 3.6. All right, so now we have our situation. Okay, so let's write down the initial velocity is 138.9 I plus 0 J meters per second. Our acceleration vector is okay. All right, so first let's find the time of flight. So the time of flight is, we'll look at the y motion. So the final y location of the object is 0 meters. The initial location is 800 meters. The initial component of the y component of the velocity is 0 minus 9.8 divided by 2 t squared. Okay. And we know what the negative solution means. We won't even write it down. Okay. So it's in flight 12.8 seconds. So when you dropped an object from a height of 1 meter, roughly the height of this table, it was in air half a second. Okay. You drop it from this height, it's in air 13 seconds. Okay. Now let's look at the x motion. All right, the final x position is what we want. Initial x position is 0 meters. Initial x component of the velocity is 138.9 and 12.8. And the x component of the acceleration was 0. Yes, so this is where it falls. All right, so it falls 1,800 meters away. 1,600 meters is a mile, so roughly a little over a mile away. Okay. And right, so this speed is roughly the speed at which a jet comes into land. 800 meters is when you see those riddle planes flying on the beach. Well, rough, or yeah, somewhere there. So if a passenger plane dropped a package from that height, that would land a mile away. Yeah. I mean, this sort of stuff is relevant because when they drop care packages and stuff like that, you have to know where they'll fall and all that. All right, so now we'll make it slightly more complicated. A projectile is launched at an angle of 30 degrees and lands 20 seconds later. Okay. So you saw that 500 kilometers per second, it lands 13 seconds later. So if you launch it from here, that would have been in flight 26 seconds. Okay. So you're launching it at quite a large speed for the projectile to be in air 20 seconds. Okay. And lands 20 seconds later at the same height as it was launched. What is the initial speed of the projectile? What is its maximum altitude? What is the range? Calculate the displacement from the point of launch, okay, to the position on its trajectory at 15 seconds. Okay, so they're asking us to do quite a bit. So again, we'll set up our problem like so. Okay. You're going to launch it at V0 at 30 degrees. Okay, we are assuming there's zero air resistance. Okay, and so on. Okay, so X, Y. So the initial velocity vector is V0 cosine 30I plus V0 sine 30J. Okay. Your acceleration vector is 0I minus GJ. Okay, so you launch it and it hits ground 20 seconds later. Okay, so we can find what is the initial speed of the projectile. So let's look at the y motion. Y minus y0 equal to v0 y t plus 1/2 ay t squared. All right, you'll see in a second why I chose this. You know the final y position, you know the initial y position, you know you don't know the initial y component of the velocity is known in terms of this initial speed, and you know the time. Okay, so you can calculate the initial speed. So 0 minus 0, I'll just write 0. 0 equal to v0 y is 0.5 v0 times 20 seconds minus 1/2 times 9.8 times 20 seconds squared. So there is your initial speed. Okay. So 10 v0 equal to 4.9 times 20 squared, which is 400. So v0 is so 49 again. 40 times that, so 196 meters per second. All right, so from the y motion, we were able to calculate the speed. Okay. What is the maximum altitude? So they're asking us to find this height it goes. Okay, and you can look up this formula from your notes. It's v0 sine theta square divided by 2g. Yep. So we have the initial speed, which is 196 meters per second, sine 30 square divided by 2. So it goes up 500 meters. Okay. See what is the range? Is that what they ask you? That's the range. Okay, you can look up the range formula or you can calculate it like so. Okay. So this is 0. X is V naught. X is 0.87 times 0.87 times V naught. And T, the time of flight, was 20 seconds. And this term is 0. Okay. So that's the distance it travels in the horizontal direction. Okay, that's 3 kilometers, a little over 2 miles.
Where do you keep getting the 20 from?
That's the time of flight.
20 seconds.
Calculate the displacement from point of launch to the position on its trajectory at 15 seconds. So at 15 seconds, it'll be somewhere there. And I want you to calculate this vector. Okay. And so what you have to do is really calculate the x component and the y component. Okay. So x minus x naught. Okay, so now you're calculating x naught is 0.87 into 196, and you're calculating it at 15 seconds, so that's the x coordinate of your position at that time. And the y position is so y equal to 0.5. Vy is 0.5 times 196, which is 98, times 15 plus minus 1/2 divided by times 9.8 times 15 squared. All right, so your displacement is 2,558 I plus 368 J, and in meters. So that's where you're located 15 seconds after you were launched. Yep.
Where's the 98 for the first part of the Y component?
This guy is half of V naught. half of that is 98. V naught times sine 30.
Okay.
Yep.
Where did the 15 come from? That makes sense.
Mm-hmm.
Makes a lot of sense.
All right, so again, let me point out. So what are we doing in all these problems? The acceleration is constant. And all we're doing is using these equations, these kinematic equations. A is constant. Okay, so these are the three equations that we use, and you apply this to the x motion and the y motion. Okay? And you use one of these three equations depending on what it is that you're trying to solve for. Okay? So if you're going to use this equation, there's one unknown and the rest is known, and so on. Okay? In general. All right, so let's solve this problem. So a projectile is shot. So when they say a projectile, what is it that they mean? Well, so it's when they use that term, you're shooting something, but they're also saying that it's only moving under the influence of gravity, air resistance is negligible, it's going on a parabolic trajectory, and so on. Okay? It's shot at a hill, the base of which is 300 meters away, so this is 300 meters. You shoot at a 60-degree angle with an initial speed of 75 meters per second. The hill can be approximated by a slope at 20 degrees to the horizontal relative to the coordinate system shown. Okay, so there is the equation of this straight line. So that's the equation of that straight line. Y equal to mx plus b. Okay, this is so that would be the y-intercept. So if you extended it there, the y-intercept is at minus 109 meters. Okay, so let's write down that equation. Okay. All right, so you've shot this projectile. The hill can be okay. Where on the hill does the projectile land? So they want you to find the x and y coordinates of the landing spot. Okay, so the x coordinate would be that, and there is the y coordinate.
Is it minus 190 or minus 111?
Okay, so we want to find the x and y coordinate of the landing spot. All right, so let's again. So for all these guys, you want to write the initial velocity and the acceleration. What is the initial velocity? 75 cosine 60 I plus 75 sine 60 j. And what is our acceleration vector? It's 0I minus 9.8 j. All right, so now let's write down the x component, y component of the motion, y minus y naught equal to v naught y t plus 1/2 ay t squared. So y naught was 0, v naught y is 65, t, ay is negative 9.8, so this is minus 4.9 t squared. Okay, so there's the y component of the motion. So this gives you the y coordinate of the landing spot. Okay. So now you want write down. So x naught is 0. This is the x coordinate of the landing spot. V naught x is 37.5 t, and ax is 0. So there's the x coordinate. Okay, so we want to find this and that. All right, looks like we have a problem here. We have 3 unknowns, and we have 2 equations. 1, 2, 3 unknowns.
The y-axis.
Very good. There is the third equation. The x and y coordinate of the landing spot are related. They're on this line. Okay, so there is the third equation. Okay, so we have been saved by a friend here. Okay, so we have 3 equations and 3 unknowns. Okay, and you can solve this. All right, so what are we going to do? How are we going to solve this? Okay, what we can do is put this information in here. Okay, again, you'll encounter this kind of stuff all the time. So you'll have 3 unknowns and 3 equations. You reduce it to 2 unknowns and 2 equations, and then reduce that to 1 unknown and 1 equation. And this is what you solve. Okay, so all your techniques that you learn are essentially this. Okay, so what we could do is we could put for x in there. This becomes an equation in t, and then here's another equation in t. We'll equate this to that, and then you'll get 1 unknown and 1 equation. Okay, so let's do that. So y equal to 0.36, and again there's multiple ways of doing this, so I'm just showing you one way, whatever has come to the top of my head. Okay. So okay, so putting this information in here gave us this equation, and now you'll see that I'll equate this to that. Y is equal to that, and y is equal to this. So 65t. So equating those two tells us 65t minus 4.9 t squared equal to 13.5t minus 109. there's that one equation and one unknown, and now we can solve for t. Okay. So this is just a quadratic equation, so 4.9 t squared minus 65 minus that is 51.5 t minus 109 equal to 0. Okay, the positive solution is what we want. You guys know that the negative solution would be it if it had started here at minus 1.8 seconds, it would be here at 0 seconds and so on. That's what that solution is. Okay. Yeah, so we have the time now, and now we can calculate the x and y coordinates. Yeah.
Could you just show me where you got the 13.5 t minus 109?
A third of this is 13.5. All right, now that we have t, we can substitute it in here, calculate the y coordinate, put it in here, calculate the x coordinate. Okay. So now, as a check, what should be true? For the x coordinate, we had better get more than 300 meters. Okay. All right, so let's do that first. X is 37.5, t 12.3. Okay. And what is the y coordinate? It's 65t minus 4.9 t squared. So yeah. So that's where it's located. Okay. Or so there's the position vector. Okay, I will solve two more problems and we'll take a break. Do you guys know what a geosynchronous satellite is? What is it?
It's kind of an orbit, so that the amount of time it takes it to go around the Earth is exactly the amount of time it takes the Earth to spin one, so it stays at the same spot like the Earth.
Right, so, yeah, so you can say the complete story, yeah, so let's say this is the Earth spinning like that. It, like our friend said, it takes 24 hours to go around once, okay? Now, the orbital period of a satellite will depend, the further out you are, the longer it takes you to go, okay? So, and it turns out that for a geosynchronous satellite, the orbital radius is 42,000 kilometers. So from the surface, you're 3,600 kilometers, about 5 radius. This takes you 24 hours. This takes you 24 hours. This takes you 24 hours. So for you to remain at the same spot, what you have to do is, you can't be like that. You have to go right above the equator and go in the same direction as the Earth spinning. Okay, that is a geosynchronous satellite. And why is that useful? GPS satellites are 12,000 miles up. That thing is useful for TV signals. Okay? So you bounce off signals like that, other communication. So you can charge people $800 a month for, $80 a month for your channel service. You know? Now, this signal takes 1.6 seconds to get back to Earth. So you can't use that for telephone conversations. Okay? For telephone conversation, hello, and then somebody says hello, you get bored. Okay? So what do you do for satellite phones?
Use closer satellites?
So there you go. You have to have a constellation of closer satellites. What's the problem with that?
You need a lot of satellites.
Well, you do need a lot of satellites. The closer they are, they decay and then they fall off, and so it's expensive to maintain that network. Yeah, so satellite telephones are expensive. All right. So a geosynchronous satellite. And by the way, so here's the Earth. So above the equator is where you're going to park your satellite. Okay. There's a satellite here. There's a satellite here. There's 720 parking spots. That's the most expensive parking spot on Earth. Yeah. Every country has their own. See, there's a good image. See all those satellites? How come there's multiple satellites there? Want to get into a problem? So here's one satellite, here's another satellite. If they're close enough, you shoot a beam. Have you seen a laser beam? See, the dot gets bigger the further out it travels. Even a laser beam spreads out. So you send a beam, a TV signal, and that beam spreads out. You don't know if you're hitting this guy or this guy. So how come they let you park? How come you have all these satellites very close by? You talk in different bands. One talks in English, one talks in Spanish. Okay. All right. So again, these are very so these are allocated to countries, the spots. All right, so a geosynchronous satellite orbits Earth at a distance of 42,250 kilometers. Okay. So the orbit is, again, so the radius of the Earth is 6,400 kilometers, and this radius is 42,250 kilometers. As a period of 1 day, what is the centripetal acceleration of the satellite? You saw that the centripetal acceleration is v squared by r, in the radius of the orbit. What is v? The speed is 2 pi r, the circumference, divided by the period square. And that's r square. One of the r's cancels, so this is r divided by t squared. And that is an acceleration. Acceleration as units of meters per second squared. Yeah. The radius is 42,250 kilometers. That's in meters. A day is 24 hours, 3,600 seconds squared. So the centripetal acceleration, which is also the acceleration due to gravity at that location. Okay. What is the acceleration due to gravity on the surface of the Earth? 9.8 meters. So as you go higher, the acceleration due to gravity decreases. And so now you'll know what is the acceleration due to gravity at this height. Okay, so it's 0.1 meters per second squared at that height. Okay. All right, we'll do one more problem and then we'll take a break. Okay, I might go a little over on the lecture, but I'm going to finish the chapter 5 lecture today. So a river is moving east at 4 meters per second. A boat starts from the dock heading 30 meters north of west at 7 meters per second. Okay, so So boat is starting heading 30 meters north of west. So 30 degrees north of west at 7 meters per second. If the river is 1800 meters wide, so a little over a mile wide, what is the velocity of the boat with respect to the earth, and how long does it take the boat to cross the river? Okay, so velocity of the boat with respect to water, velocity of with respect to the ground is equal to velocity of boat with respect to water plus velocity of water. Okay, so what this means is this is the velocity of the boat with respect to ground. That's what those subscripts mean. And remember, in what you can do is add a letter in between. So this is the velocity of the boat with respect to water, and the velocity of water with respect to ground. What is this guy? That's the velocity of the boat with respect to water. And what is this guy? That's the velocity of water with respect to ground. So this velocity plus this velocity, that velocity gives you the ground velocity of the boat. Okay? Did you guys understand that? So if the river is flowing this way and you point your boat in this direction, the river drags you along like that, and so here is your net velocity. Yeah. So in diagrams, here is the velocity of the boat with respect to water, and there is the velocity of the water with respect to ground, and this will be the velocity of the boat with respect to the ground. Okay. So now, of course, when we want to add vectors, what is it that you want to do? You want to write those velocities in component form. -7 cosine 30i plus 7 sine 30j. Okay, this vector is that. And the velocity of water with respect to ground is just 4i plus 0j. Okay. So now we're going to add the two vectors. So the velocity of the boat with respect to the ground is this vector okay, so it's minus 2.06 I plus 3.5 J meters per second. All right, so what you've done is this is the X direction, there's the y direction. You want to cross the river, you want to travel in the y direction, okay? So y minus y naught equal to v naught yt plus 1/2 ayt squared. Okay, so y is 1800 meters, the final y coordinate, initial y coordinate is 0. Your y component of the velocity is 3.5 meters per second. That's the velocity with respect to the ground. What was the acceleration in the y direction? So this, your boat, you're not zero. You're not accelerating. This is 0, okay? So t is 1800 meters divided by 3.5 meters per second, and you get in seconds, okay? So 515 seconds or 8.6 minutes, okay?